In this lecture, we'll delve deeper into vector spaces and subspaces. So far, we've seen how to solve systems of linear equations, and in the last video, I defined what fields are and what vector spaces are, and we saw some examples of fields and vector spaces. In this lecture, we'll go into more details about vector spaces. In particular, we'll see what linear combinations of vectors are and how they can generate vector spaces and subspaces. And in relation to this, we'll see two vector spaces associated with a matrix, which will be particularly important in the context of solutions of systems of linear equations. So we've already seen what a vector space is. A vector space is formally defined as a tuple, consists of a non-empty set V, and the vector space is always defined over a field. The field has associated addition and multiplication operations, and corresponding, so the vector space has two operations, vector addition and scalar multiplication. The vector addition helps you add two vectors together, and scalar multiplication helps you multiply a vector by a scalar from the field, right? So if we have two vector spaces v1 and v2, v1 and v2, and they're both defined over the same field, say f, and if v1 is a subset of v2, then we say that v1 is a vector subspace of v2, or v1 is simply a subspace of v2. So let's see an example. So let's take v2 to be, say, R3. So this is the set of all vectors of length 3, a, b, c, such that a, b and c are in R, right? So can you think of one vector subspace of R3? So you can pause the video and try to come up with an example which of some subspace of R3. Okay, so here's an example of a subspace of R3. So let's define v1 to be set of all a, b, 0, such that a comma b are in R, right? So clearly v1 is a strict subset of R3 because the third component is always 0, but the first two components can be chosen freely. So this is one example of a subspace of R3, and as we and later in this video we'll see more examples of subspaces. Right? So we've defined what a vector space is. A vector space was defined through a number of properties, including commutativity and various properties of vector addition and scalar multiplication, including commutativity, the existence of identity, inverse, and then distributivity, and so on, right? But then so if we have, say, a vector space v1 over a field f, and we are given an arbitrary subset v2 of v1, then how do we test whether v2 is a subspace of v1? Of course, one way is to check whether each of the properties of a vector space is satisfied, but there's actually an easier way, and I claim that if v2 is a subset of v1, then v2, so v1 we know is a vector space, defined over a field f. So if we know that v1, if we know that v2 is a subset of v1, then I claim that v2 is a subspace of v1 if and only if the following property is satisfied. So for all vectors v1, v2 in this set v2, capital V2, we have, and for all alpha in the field F, v1 plus alpha v2 is also in the set v2, right? So I claim that this test of v1 plus alpha v2 being a subset, being in v2, is a necessary and sufficient condition to test whether v2 is a subspace of v1. So maybe let's see an example. Okay, let's take v2, let's take v, or here what have we taken? Yeah, so let's take v1 to be R3 and v2 is the set that we've seen previous. So let's take another example. So v1 is R3 and v2 is the set v1, okay, let's take a plus b 3a b. Okay, so such that a comma b are in R. So the question is this set v2 a subspace of v1 or not? Let's see if the test is satisfied. So if we consider any v1 to be equal to a1 plus b1, 3a1 and b1, v2 is a2 plus b2, 3a2 b2 for some a1 b1 a2 b2, and if you look at v1 plus alpha v2, then we have v1 plus alpha a2 plus b1 plus alpha b2, then we have 3 times a1 plus alpha a2 and b1 plus alpha b2, right? So in other words, v1 plus alpha v2 is also of the same form as this a plus b 3a b. So if I call this v1 of a1 b1, if this is v2 of a2 b2, then v1 plus alpha v2 is v of a1 plus alpha a2 b1 plus alpha b2. So in fact you can test that. So clearly this is also, so this vector, so the resulting vector is also of the same form as a plus b 3a b, where a is equal to a1 plus alpha a2, b is b1 plus alpha b2. So this is also in the set v2, and therefore this is also and by our proposition by this property that we have over here. This is a vector space over F, right? And to test whether that this is indeed, that V2 is indeed a vector space, you can check whether all the properties are satisfied or not. So let's maybe see a quick proof of the fact that V is a vector space. Okay. So firstly, if V2 is a vector space, or if it is a subspace of V1, then clearly this property is satisfied, right? So let me call this property So what is this property? This is the property that V2 is closed under linear combinations, right? So V1 plus alpha V2 is a linear combination and of V1 and V2, and this says that this should be closed under linear combination, right? So let me call this property P star. Okay, and if V1 is a vector space, then clearly P star must be satisfied. Why is that? Because V2 is also a vector space, and therefore any vector space is closed under addition and scalar multiplication. So if V2, if little v2 is in capital V2, is in the vector space V2, then alpha V2 should also be in the set capital V2, and therefore since V1 and alpha V2 are in the set V2, V1 plus alpha V2 should also be in the set V2, right? Then so clearly if V2 is a subspace of V1, then P star is satisfied. Right? So this is the easy part. To prove maybe the slightly harder, what we also want to show is that if property P star is satisfied by V2, then V2 is a subspace of V1. So we know that V2 is a subset of V1. We have to prove that V2 is a vector subspace of V1. And to show this, all we need to do is prove that V2 is also a vector space, right? And to prove that it is a vector space, we need to show that every property is satisfied, right? So what properties need to be satisfied? Firstly, they need to be closed. So suppose that V2 satisfies. So firstly, V2 is a subset of V1. Suppose that V2 satisfies property P star. That is, for every vector V1, V2 in capital V2 and alpha in the field F, V1 plus alpha V2 is also in capital V2. Right? So suppose that this is satisfied, then does it satisfy, then does capital V2, then is capital V2 a vector space? So firstly, so this obviously implies that this is closed. So it's closed under addition and scalar multiplication. So closure property is satisfied because V1, V2 belongs to capital V2 implies that V1 plus v2 is also in capital V2, we can simply take alpha to be equal to 0. And similarly, it is also closed under multiplication, because if v1 belongs to v2, then alpha times v1 is also in capital V2. We can simply take v1 to be the 0 vector, right? So firstly, so even before that, can you always conclude that the 0 vector is in capital V2? So if this property is satisfied, then can you always say that the 0 vector is in capital V2? So pause this video for a moment and think about it. Right. So indeed, if V2 satisfies V star, then the 0 vector is in V2, because you can take any vector little v2 multiplied by 0 and you will get the 0 vector. Right? So the 0 vector is always in V2. Okay, so what all properties do we need to satisfy? So we want to make sure that closure is satisfied, and then what else? You need to make sure that it is commutative, so plus is commutative, but that is a property that you get anyway from the vector space V1. So V2 is a subset of V1, and the properties of vector addition are inherited from V1, and therefore commutativity is satisfied. So is associativity. What else do we need to satisfy? There has to be the additive identity belongs to V2, and we've seen that if we take V1, if we take alpha to be equal to 0, then okay, so or there's another way to prove this. You can take alpha to be equal to -1, that is the additive inverse of the unit element. So therefore and take v1 equal to v2 equal to v, therefore v plus -1 times v should be in v2, which implies that 0, so -1 times v is -v, or another way to write it is (1 plus -1 times v). This is equal to 1 plus -1 times v, which is 0 times v, which is in v, right? So the 0 vector is in v2. Similarly, we want to make sure that every element has an additive inverse. -v is in v2, and for this we can again take v1 to be equal to the 0 vector, and v2 to be equal to v, and alpha to be equal to -1. So -1 times v is in the set capital V2. So take v1 to be equal to 0, v2 to be equal to v, and alpha to be equal to -1. So this implies that -v is in the set V2. What else do we need to satisfy? So the remaining properties are all inherited from V1. So for all C1, C2 in F, C1 plus C2 times V is equal to C1V plus C2V. So this anyway comes from V1. For all C1 in F and V1 V2 in capital V2, C1 times V1 plus V2 is C1 V1 plus C2 V2. This is also a property which comes from the space V1, because V2 is a subset of V1. And similarly for all C1, C2 in F, C2, C1, C2 times V is equal to C1 times C2. And basically closure takes care of everything else. So clearly C1 and this property is inherited from the space V1, right? So this is a proof of the fact that if this property P star is satisfied, then V2 is a vector subspace of V1. So at any point, if we are given a vector space V1 and we want to test whether V2 is also a vector space, so it's a subspace of V1, then as long as V2 is non-empty and it's a subset of V1, we only need to check for property P star to ensure that it's also a subspace. So here's an interesting class of vector spaces, and it is a space of polynomials. So suppose that we have a field F. For now, let's just take F to be equal to R, but this generalizes to any field, and define for any integer, any positive integer k, I'll define pk x to be the set of all polynomials of degree less than or equal to k and coefficients from with the indeterminate x. So in other words, this is the set of all a0 plus a1x plus so on plus ak x to the k, where ai is an element from the field for 1 less than or equal to I less than or equal to k, 0 less than or equal to I less than or equal to k. So you can prove that this set pk of x is also a vector space, right? So this is an interesting class of vector spaces which will frequently occur in which frequently occur in several applications. Another interesting vector space which is something that you would already realized by now, is the vector space of matrices. So the set of all may be denoted by m, k by n. So the set of all k by n matrices with entries from a general finite field F is also a vector space over F, right? Okay. So now that we have a vector space V, there is one very easy way to construct subspaces of V, and it turns out that these are the only ways by which you can construct subspaces of V. So this is a mechanism which lets you generate all possible subspaces of a given vector space V. So obviously the vector space is defined over a field F, and henceforth I will not explicitly mention this. So whenever I say that there is a vector space V, it means that this is associated with this is defined over some over some field F, and the associated vector space operations are also well defined. Okay, so given a vector space V, let us consider the set of all combinations. So let's consider a subset. Let me call it script V. So consider a subset of vectors V1, V2 up to Vm. So let's assume that I take m vectors from this vector space. Okay, pick any m vectors and consider the set of all linear combinations of these vectors. So take a1 v1 plus a2 v2 so on plus am vm for a1 a2 up to am in f. So this set, let me call it L. I claim that this is a vector subspace. So clearly this is a subset of the vector space V. I claim that this is actually a subspace of V, and I leave it to you as an exercise to check that this is indeed the case. And how would you test whether L is a subspace or not? You can just test for property P star, right? So this generates, so therefore v1 v2 up to vm, you can pick an arbitrary sub collection of vectors of vector space, and taking all possible linear combinations of this vector space gives you a subspace of V. But so let's see what is happening intuitively. Now let's take R3. Okay, this is my x-axis, this is my y-axis, and this is my z-axis. So I can start with a given vector. Let's take a vector v1, which is some point over here. Now if my script v is equal to v1, is equal to, this is v1, just the set v1, then what is capital L equal to? It is a set of all scaled versions. So it's a set of all a1 v1 for a1 in f. So basically all possible scalings of v1, and that is going to generate a line, right? So it's going to be a line in the direction of v1 passing through the origin. So that is going to be my L1, right? So now let's take, suppose that I take another vector v2, right? So capital V is equal to v1 v2, right? So if v1 and v2 lie along the same line, then capital L is going to be the same line itself. But then if v2 and v1 are not collinear, then capital L, or the vector space or the subspace generated by v1 and v2, is going to be the set of all linear combinations of v1 and v2, and that is going to be a plane, right? So it's going to be some plane passing through v1 and v2. So in general, if you have say k vectors or m vectors in Rn, and you take the set of all linear combinations of these, this is going to be some kind of a hyperplane passing through the origin, and the dimension of the hyperplane will be less than or equal to m, right? So clearly, taking linear combinations of vectors of a vector space is going to give you a subspace of V. But in fact, as we'll see a little later in a future video, this is the only possible way of generating subspaces of V. There is no other way you can generate a subspace of V. Okay, so in this context, let's see an interesting vector space. So given a matrix A, the column space of A. Okay, so let me just back up for a moment to just introduce some notation. So given a set of vectors v1, v2 up to vm, you take the set of all linear combinations of these vectors, then we get a subspace, and we call this subspace as the subspace generated by v1, v2 up to vm. Okay, and we say that v1, v2 all the way up to vm are generators of the subspace L. Right. So the column space of so given a matrix A, the column space of this matrix is the vector subspace which is generated by the columns of A. So if you have columns C1, C2 up to Cn, assuming that this is an m by n matrix, each Ci is going to be an m length vector, then the column space is of A is the subspace generated by the columns C1, C2 up to Cn. Right? So we say that this is a subspace generated by C1 through Cn, or also sometimes the subspace spanned by C1, C2 up to Cn. So generated is the same as spanned. Right? And we call L, this set L over here, as the subspace generated by v1 through up to vm, or the subspace spanned by v1 up to vm, or also sometimes the span of v1 up to vm. Some people also add a qualifier saying that this is the linear span of v1 up to vm, but at least in this course we're only dealing with linear systems. So whenever I say it is a span of v1, v2 up to vm, then I mean the vector subspace which is generated or spanned by v1 v2 up to vn. Okay, so what does this mean? What does the column space have to say about a system of linear equations? So in general, a system of linear equations can be given by ax equal to b, and a solution exists only if there exists an assignment x such that ax is equal to b. So in other words, in terms of the column space, and this really comes from the column interpretation that we saw in the very first lecture, in order for this system to have a solution, there must be an assignment x which satisfies ax equal to b, or in other words, b must be in the column space of a, right? So b must be, so by definition, for this to have a solution, b must lie in the column space of a. So for solution to exist, b must lie in the column space of a, because some linear combination of the columns must give you b. If no such linear combination exists, then it means that there exists no assignment for x which satisfies this system, right? So that is the importance of the column space or the columns of a in terms of a system of linear equations. Now we've seen one way to generate a subspace of a vector space. We now see another way to generate a subspace. Right? So another way to generate a subspace of a vector space is the following. So suppose that I have a system of, suppose that I have a matrix A. This is an m by n matrix, right? Let us consider I'll define capital N of A to be the set of all vectors x in, so A is an m by n matrix, so it is a set of all x in Rn such that A times x is the zero vector, 0 n, right? So this set is what I call the null space of a matrix A, right? And I want you to pause this video for a moment and show that the set n of A is indeed a vector space. It's a subspace of Rn. Okay, so hopefully you have the proof, but here it is anyway. So suppose that to show that n of A is a subspace, you need to show property p star. So if you take any two vectors v1 and v2 which lie in n of A, and take any alpha in the field, and you take v1 plus alpha v2, okay? So you have to prove that, to prove p star, you have to prove that v1 plus alpha v2 also lies in n of A. And how do you show this? Take A times v1 plus alpha v2. This is equal to av1 plus alpha av2 by basic properties of matrix multiplication. But we know that av1 is 0 and av2 is also 0, so this is also equal to 0. So this implies that v1 plus alpha v2 is also in N of A, and therefore N of A is a vector subspace. So now, associated with a matrix, we've seen two different subspaces, the column space and the null space. But one very important thing to note is that the column space for a general M by N matrix, the column space is a subspace of Rm. Right? This is the space spanned by the columns of A. So obviously this is a subspace of Rm. Whereas the null space is a subspace of Rn. So you get this from the rows. So at the face of it, there doesn't seem to be an obvious connection between the column space and the null space. But in fact, we'll see in a moment, and also in the lectures to come, how these two are very intimately related. So firstly, we've seen that the column space tells you something about the system of solutions of a linear, the set of solutions of a linear system. A solution exists if and only if the vector B lies in the column space of A. But what does the null space say about the number of solutions? So the column space says whether there exists a solution or not. So if B lies in the column space of A, right? So if B lies in the column space of A, then there exists at least one solution. Right? So there may be infinitely many solutions, but there exists at least one solution. The null space tells you whether the number of solutions is infinite or not. So, and why is that the case? So suppose that the null space, so obviously note that the null space is always non-empty, because the zero vector is always in the null space, right? If you have non-zero vectors in the null space, then clearly, so suppose that AV is equal to 0 for some V not equal to 0. Okay, suppose that we have some vector V such that A times V equal to 0 for some V not equal to 0, and suppose that there exists a solution AX equal to B, right? Then I claim that that if this property is satisfied, and if there exists at least one solution for AX equal to B, then in fact there are infinitely many solutions for AX equal to B. And why is that the case? Note that if you take any scalar alpha, any number alpha, and consider x plus alpha times V, then x plus alpha times V is also a solution. Why is that? If you take A times x plus alpha times V, then you get AX plus alpha times AV. We know that AX is equal to B, and A times V is equal to 0, so you get 0. So this is B. Therefore, if X is a solution, then X plus alpha times V is also a solution for every real number alpha and for every V in the null space of A. Therefore, if the null space contains only the zero vector, then there exists a unique solution. If the null space contains vectors other than the zero vector, then there are infinitely many solutions for the system. And we'll formalize this, we'll prove this in more detail in the coming lectures.